Many thanks to the organizers for organizing the meeting, and thank you for having me. I'm going to talk about Nondisjoint CDSAT, arrays, maps, and vectors with abstract domain. And this is joint work in progress with Stefan Graham-Lengrand and Natarajan Shankar. Now, arrays are a well-known data structure in programming languages, which is characterized by direct access to values, to elements, through indices. The basic operations, accordingly, are read and write, read an element or write an element, that are also called select and store. And this theory gets formalized, gets presented as a first-order theory for the purpose of automated reasoning, specifically satisfiability modulo theories, as a theory with sorts for indices, values, and arrays. And with axioms, there are two so-called select over store axioms that say how the select and store operation interplay. So if we store a value in array I, in array A at index I, and then we read the same index I, we get the value we just wrote. On the other hand, if the indices I and j are different, and we store a value at index I, and then we read at index j, we get the value in the original array independent of the store. These axioms have been around since the early 60s. They are usually attributed to John McCarthy in an old paper. And then there is also an extensionality axiom, which allows to say when two arrays are equal, and two arrays A and B are equal if they have the same value at all indices. This theory is not decidable, but its quantifier-free fragment is, and therefore there are decision procedures, and it is widely implemented in SMT solvers. It has been considered a useful theory to reason about computer memory in program verification, precisely because it has these basic operations, read and write, that are similar to the basic operations we do in the computer memory. However, arrays in programming languages are finite. And for example, in most programming languages, they are assumed to have integer indices ranging from 0 to say n-1 if n is the length of the array. Other arrays are different. They have indices not starting necessarily at 0. But anyway, in programming languages, arrays are typically finite, as the computer memory is finite. On the other hand, in the theory of arrays, arrays are finite or infinite depending on the cardinality of the set used to interpret the sort of indices. For example, if we take the set of the integers, we have infinite arrays, because there is nothing in the theory that makes the structure finite. Now, there is an extension of the basic theory called the array property fragment, which is, well, it's not an extension of the theory, sorry. It is an extension of the quantifier-free fragment, because it allows a limited usage of quantification only over variables of sort index. And using quantifiers in this limited manner, it is possible to write properties about arrays, such as bounded equality. So it is possible to say that two arrays A and B are equal if they have the same values at all indices between a lower bound L and an upper bound U. Then it is also possible to define sortedness and other interesting properties. This fragment is decidable because it is possible to compute finitely many instances of the quantifiers over variables of type index, of sort index. And then the problem after the instantiation can be fed to a decision procedure for the disjoint union of arrays, integers, linear integer arithmetic, and the theory of values. So in some sense, one could think that the issue of finiteness of arrays is addressed to some extent by this notion of bounded equality. So so if the sort of indices is infinite, such as the integers, the arrays are infinite, but we can talk about a finite segment between two bounds, lower bound L and upper bound U. However, this fragment is decidable, but it requires to reason about quantifiers, which is often not considered as still sufficiently efficient in SMT solvers. So another possibility would be to add a length function to the theory of arrays, add to the signature a function len, which maps every array to its length. And then we could revise the extensionality axiom and say that two arrays A and B are equal if they have the same length, and if they have the same values and all the indices comprised between 0 and the length itself excluded, so strictly smaller than the length. Now, there is a problem with this kind of axiom, and that is that the two theories that are involved, namely the theory of arrays and the theory of the integers, linear integer arithmetic, are no longer disjoint if we add this axiom to the theory of arrays, because this axiom involves the ordering on the integers. Two theories are said to be disjoint if they do not share any symbol other than equality. If we put in a theory an axiom that uses symbols from another theory, the two theories are no longer disjoint. And what is the problem? The problem is that most methods for reasoning in combinations of theories assume that the theories are disjoint. So this kind of axioms are considered problematic. This is actually a fairly general phenomenon with the length function, because also with lists, if we define a length function over the constructors for non-empty lists, and we say the length of the empty list is 0, the length of a cons of an element with the list is 1 plus the length of the second argument of cons, these two axioms force the theory of lists and the theory of the integers to share symbols, because the 0, the 1, and the plus appear also in the presentation of the theory of lists. Now, this is a well-known phenomenon which has been studied by several authors. These functions are called bridging functions, a name that was introduced by Viorica Sofronie Stockermans already in 2009. Not only length of arrays or lists, but also the size of trees or the height of trees are bridging functions. And they appear, for example, in recursive data structure, also known as absolutely free data structures, such as lists of trees, where they were studied by Paola Chocron, Pascal Fontaine, and Christophe Ringuysen in a JAR paper in 2020. There is a difference between recursive data structures and arrays. In recursive data structures, the bridging axioms are those that define the bridging function over the constructors. In arrays, the bridging axiom turns out to be the extensionality axiom, as in the example I gave previously. But the phenomenon is the same. These bridging axioms make the theory non-disjoint, which is difficult for theory combination. So we have either quantifiers or non-disjoint combinations. What else? There are also other theories in SMT. People have been studying theories of strings and sequences that are, of course, interesting in their own right. Strings are sequences of elements from a finite alphabet. Sequences are viewed as a generalization of the theory of strings, where the elements do not necessarily come from a finite alphabet, such as an alphabet of characters, but they come from a sort of elements that can be interpreted with any set, including, of course, infinite sets. And usually in a theory of sequences, we are going to have a symbol for the empty sequence, a binary symbol for associative concatenation, so that we get a monoid. And then different symbols may be added, such as a unary constructor wrapping a single element into a singleton sequence, an extract function that returns a subsequence, an access function that returns an element in a position, and a length function that gives the number of elements in the sequence if the sequence is finite. Now, there have been approaches that propose to use sequences to model finite arrays. Now, this is a little bit counterintuitive because, as I said, in programming languages, arrays are natively finite. But then when we formalize arrays as a theory, the number of elements is given by the cardinality of the set that we use to interpret the sort of the indices. And if we use integers, we get infinite arrays. Now, in mathematics, usually people think of sequences as being possibly infinite. So it is a little bit of a tour de force to use sequences to model finite arrays. And nonetheless, it has been done. There was a work by Sheng and others at ICHCA 2022 and then on JAR 2023, where they defined sequences of integer indices, finite sequences with the indices ranging from 0 to the length -1, precisely because they wanted to model arrays in reality. They added an update function, update of a single element, so that access and update mirror, select and store, an extensionality axiom, which is the same as in array with length. And the way they dealt with non-disjointness, they didn't really give a method for a combination of non-disjoint theory, but they view the theory of sequences as an ad hoc conservative extension. Conservative means that satisfiability doesn't change, of the theory of the integers, and then gave two inference systems, one actually based on string reasoning and the other based on array reasoning that mirror the procedures they have in CVC5 to reason about these sequences. Another approach was proposed by Hichem Aïd El-Ara, François Bobo, and Guillaume Bourri at SMT 2024, and then in Hichem thesis. They are interested in ADA arrays, and therefore they consider sequences between generic indices n and m. Sequences do not necessarily start at 0, and therefore they call them m sequences. And they add functions first and last to get to the first and last index, relocate to shift the sequence. It's possible to update the whole subsequence at once. There are a lot of function symbols, and an extensionality axiom using first and last in place of length. Now, there is a problem with this approach using sequence. The quantifier-free fragment of the theory of arrays is decidable. It is not known whether the quantifier-free fragment of these sequences is decidable. And in the papers and in the thesis, they only have soundness result. They have neither proof of termination of the procedure nor completeness. So let's recap. We start from arrays in programming language. In programming languages, they are finite. We have a theory when they are not necessarily finite. The cardinality depends on how we interpret the sort. There are various solutions. Array property fragment, you need to reason with quantifiers. Bridging function, you need to address a non-disjoint combination. Sequences, you probably lose decidability. The point is not settled, but there are simpler theories that are already known to be undecidable in the quantifier-free fragment. Now here I'm proposing a different solution. I'm proposing a theory of arrays with abstract domain, where we can reason about finite arrays with no need for quantifiers, unlike in the array property fragment. We do get a non-disjoint combination of theories, but we can reason about it with the CDSAT, which is a method for a theory combination that requires neither stable infiniteness nor disjointness, because it allows theories to share predicate symbols other than equality. And the quantifier-free fragment of this theory is decidable. as the quantifier-free fragment of the basic theory of arrays. So let's see what this theory looks like. In the signature, we are going to have the usual sorts, indices, values, arrays, but also length. And we are going to have a length function that we add to select and store. And then most importantly, we add an admissibility predicate, which says when an index is admissible with respect to the length of the array. So adm IL says that index I is admissible with respect to the length L. Now, the formula that defines this admissibility predicate defines the abstract domain of the array. And then when we give an interpretation of the sorts, so we say what are indices, for example, the integers, what are lengths, for example, the integers, and so on, we get a concrete domain, the set of the admissible indices. Now, this symbol admissibility will be shared because the theory of arrays with abstract domain does not define it and let another theory T provide its definition. In terms of presentation, we have the select over store axioms, but there is a change because we have the notion of whether indices are admissible or not. So the first select over store axiom, the one that says what happens if you read at the same index where you just did a store, changes, because now we say that if we take an array A and store the value V at index I, and then we read at index I, we get the same value if the index is admissible. What if the index is not admissible? Then the store operation has no effect. So we don't care what happens outside of the domain of admissible indices. The other select over store axiom remains unchanged. Also, a store operation does not change the length precisely because a store at an index which is not admissible has no effect. And the extensionality axiom is written with length and admissibility. So for two arrays A and B to be equal, they must have the same length and the same value for all admissible indices. Now let's see an example. Suppose that we charge the theory of the integers to define admissibility. It interprets indices and lengths as integers, as we do in programming languages, and we can define admissibility precisely as we do in programming languages. So an index I is admissible with respect to the length n if it is comprised between 0 and n minus 1. So we get exactly what we have in programming languages. The set of admissible indices is the interval 0, n with n excluded. And under this interpretation, the extensionality axiom of arrays with abstract domain covers the extensionality of arrays with length given above, and therefore also the extensionality in the theory of sequences, the one by Sheng and others. But we can be more flexible than that. Suppose again that we entraft the definition of admissibility to the theory of linear integer arithmetic, but this time we interpret lengths as pairs of integers. Then we can give a lower bound and an upper bound exactly as we did in the array property fragment with bounded equality. So we say an index I is admissible with respect to a pair of bounds LU if it is comprised in the interval with extremes L and U, which is the set of admissible indices. Under this interpretation, the theory of arrays with abstract domain covers bounded equality, as in the array property fragment, and extensionality in the theory and sec of sequences, the second one, the one by Ait El Ara, Bobo, and Bourri. Now, we can also equip arrays with a starting address, as many programming languages do, because in many programming languages, for two arrays to be equal, it is not enough that they have the same length and the same values at all the indices allowed by the length, but they also need to start at the same starting address. So suppose that length is interpreted as a pair with the starting address in memory and the number of admissible indices, then admissibility is defined by that axiom so that the starting address does not affect admissibility. But for two arrays to be equal, they need to have the same length and therefore also the same starting address. So they really need to be the same physical array in memory because the starting address is the same. So as you can see, precisely because the notion of the domain of definition of the array is abstract and can be defined in different ways, we can cover different situations and interpretations. We can also view admissibility as membership, interpreting indices as elements of a set and length as a subset. So we say that an index I is admissible with respect to a length n if I is a member of n, and then the set of admissible indices is an arbitrary subset of a set, which doesn't have to be a set of numbers, does not have to be ordered, does not have to be linearly ordered. So we get a lot of flexibility and expressive power. We can do more, because we can also decide that when we do a store at an index which is not admissible, that index becomes admissible and therefore the data structure grows. So we define a theory of maps with abstract domain where a store at an index which is not admissible make that index and that index alone admissible so that the data structure can grow by one element at a time. This is captured by the first axiom up there, which says an index j is admissible in the array that we get after a store of value v at index I in array A if either the index j was already admissible in the original array, or else j is equal to I, because I was not admissible, but we write there, and therefore we make it admissible, and the data structure grows dynamically. Now, now it is no longer true that store does not change length. Store does not change length if the store happens at an index which is admissible. And the select over store axioms can go back to the original version because we no longer need to restrict the first select over store axiom to the case of admissible indices, since now also a store at an index which is not admissible in the original array makes sense because it writes the value and makes that position admissible. Extensionality does not need to change. We can also capture vectors as dynamic arrays by making it possible to make admissible a whole bunch of indices at a time. So if a store happens at an index I which was not admissible, not only I, but all the indices comprised between the length, the upper bound of the previous range, and I become admissible. So we say J is admissible with respect to the array resulting from the store, is either was admissible in the original array A, or else it is smaller or equal than the index I where we do the store. So now we allow the data structure to grow dynamically, not only by one position at a time, but by a whole bunch, which is actually what happens in vectors in programming languages, where vectors are defined as dynamic arrays. Now note that the theories of sequences that I considered before do not capture this behavior. But now how do we reason about these data structures with abstract domain, arrays, maps, and vectors? With CDSAT. So what is CDSAT? Whoops. Yeah. CDSAT stands for conflict-driven satisfiability, And it is a method for satisfiability modulo theories and assignment in a union of theories. So it is a method for theory combination. It works by orchestrating theory modules, one per theory, in a conflict-driven manner. It is defined as a transition system. It is a generalization of MCSAT to combinations of theories, and it inherits from MCSAT two key characteristics that CDCLT does not have, that is assignment of values to first order terms, and theory conflict explanation by theory inferences that may generate new terms. It treats propositional logic as one of the theories, so that we don't have a fixed hierarchy between the subsolvers and the decision procedures for the theories. It admits also first order assignments in the input. And it is sound, we proved it sound, terminating, and complete, not only for disjoint theories, but also for predicate sharing theories. That is, for theories that share predicate symbols other than equality. Disjoint theories share equality. Predicate sharing theories are either disjoint or sharing predicate symbols in addition to equality. And in our case, the share predicate will be the admissibility predicate. CDSAT is sound, terminating, and complete for these theories without requiring disjointness, although functions must be disjoints, only predicates can be shared, and without requiring stable infiniteness. Now, how do we fit a theory in CDSAT? So we have these new theories with abstract domain. How do we fit them in? What do we need to provide? We need to provide a theory module that is an inference system, which is an abstraction of a decision procedure. It needs to be sound. This is a basic requirement, and we need it for the soundness of CDSAT. It needs to come with a finite local basis, that is a function that, given a set of terms, returns a finite set of terms that contain all the terms that the inferences may possibly generate from those input terms. And this is for termination, because when we have a whole bunch of theories, and each of them has a theory module, and each of them has a finite basis, we have a technique to combine this finite basis, which is non-trivial, into a global finite basis to ensure that in the entire CDSAT derivation, only finitely many terms will be generated, and therefore termination will be guaranteed. And then what do we need to require for completeness? Now, the completeness of CDSAT requires that there is a leading theory, which does not need to be a real theory in the combination, but can also be a fictitious theory that we only use for the proof of completeness, which has all the sorts and all the shared predicates. So this one theory needs to have all the shared information. And then the theory module for the leading theory must be complete. The other theory modules must be complete with respect to the leading theory. What does it mean? The theory module for the leading theory must be complete. It means that when it can no longer expand the trail, just like CDCL, MCSAT, all the paradigms for SMT solving, CDSAT works on a trail following the model of CDCL, the standard models from subsolvers. So when the inference system, so what does it mean that an inference system is complete with respect to its own theory? It means that when it can no longer expand the trail, it cannot do anything, there is a model for the view of that theory of the trail. So for what is on the trail, which pertains to that theory. All these notions are precisely defined in CDSAT. And what does it mean that the theory module is complete relative to the leading theory? It means that when the theory module cannot do any inference on the trail, it cannot do any step, no decision, no propagation, no conflict explanation, nothing. Not only there is a model of that theory of what we have on the trail that belongs to that theory, but that model agrees with the model of the leading theory on the cardinality of the shared sorts, on the equality of the shared terms and on the interpretation of the shared predicate symbols. So how do we do this for the theory of arrays with abstract domain, for example? We turn axioms into inference rules, because in the practice, a theory module will be a decision procedure, but for the purpose of proving soundness, termination, and completeness, a decision procedure gets abstracted into an inference system. So we'll have, for example, rules that says if n is equal to m and I is equal to j, and I is admissible with respect to n, but j is not admissible with respect to m, we have a contradiction, obviously. It's just coming from the congruence axiom for admissibility. On the other hand, if a is equal to b, then the length of a must be equal to the length of b. And in the theory of arrays with abstract domain, a store does not change the length. So if we write that the length of a store AIV is different from that of A, we get a contradiction, and so on. Some rules will generate bottom, and they are used for conflict detection. Some other rules don't. And usually this comes from the need of balancing the design of the finite basis, because we don't want to generate too many terms, and completeness, because we do need to generate certain new terms, such as that the length of A is equal to the length of B. Well, that's another example. We take the select over store axiom that uses admissibility, and we get an inference rule which detects a contradiction if I is equal to j, and the length of A is n, and I is admissible, and B is the same as the store AIV. But then select Bj is different from V, we get a contradiction because this contradicts the select over store axiom for admissible indices. And it suffices to have B equal to store AIV and select Bj different from V, and not necessarily the nested term. So terms can be also flattened. Now, how do we get, for these theory arrays with abstract domain, the completeness argument intuitively? Think how we interpret the sort of arrays. For now, just basic arrays without admissibility. We interpret the sort of arrays with a set of functions. So we view in the model an array as a function, a map from indices to values. But arrays are data structures and they can be modified, whereas functions are mathematical objects that do not change. So the interpretation of the sort of arrays is an updatable function set, that is a set of functions such that for every function that we use to interpret an array, if we do finitely many changes, finitely many updates, we find another function in the same set that can be used to interpret the array after the changes. So the function is still a member of the set. Now, when we add abstract domain, how does this interpretation change? It's very simple. We are going to consider partial functions because we only need the function to be defined on the admissible set of indices. Of course, in the model, the select, store, they are all interpreted totally, only we are not interested in what happens to the array outside of the admissible set. And then to interpret arrays, we use not just one set of functions that is updatable in the sense that if we make finitely many changes, we still find the function in the same set to interpret array, but a collection of them, one for every value of the length in the interpretation. So we proved that the theory module for the theory of arrays with abstract domain is leading theory complete for all leading theories that are suitable in the following sense. The leading theory needs to have all the sorts of the theory of arrays with abstract domain. It needs to share with the theory of arrays with abstract domain the symbol of equality, of course, and the admissibility symbol. And for every model of the leading theory, there exists a collection of updatable function sets, xn indexed by the values for the length, such that if f is a function in one of them, such that what do we have in these sets? We have functions that are partial, so from admissible indices to values, according to the interpretation in the model of indices, admissibility, and values. And the sum of the cardinalities of these sets will give us the cardinality of the sort of arrays. Now, suitability does not really restrict combinability because, again, this is only a machinery for the completeness proof. Now, in CDSAT, we also have proof generation. This I must say because this whole meeting is about proofs, although I brought you a little detour into reasoning about data structures. So we have a proof carrying version of CDSAT, which, assuming that the theory modules produce proofs, carries proof terms, which can then be reconstructed into proofs, for example, resolution proofs. Or else it can be defined a trusted kernel of primitives, and then we can have an LCF style approach. In current work, we are defining theory modules for maps and vectors, and we are proving their leading theory completeness. So we did it for arrays. Maps and vectors are still current work. In the longer term, we are interested in investigating whether it is possible to enrich arrays with abstract domain with a concatenation operation, which would allow us possibly to subsume the theory of sequences we saw before. Then, of course, concatenation is an ugly beast for decidability, so we would have to see whether the quantifier-free decidability remains or not. There exists a baby CDSAT-based verified solver in Rust called Sprout, which hopefully will be completed at some point. This is work by Xavier Denis. And we also, in the future, we also plan to investigate handling of quantifiers in CDSAT. We have another method called QSMA for quantified satisfiability modulo theories and assignment. It is only for a single theory, which must be complete. We applied it only to the fragments of arithmetic. So it is still open territory to see whether it can be integrated in any way with the CDSAT. Now, CDSAT has been around since CADE 2017. There are 2 papers on JAR, the long versions of conference papers at CADE 2017 and CPP 2018. In particular, the treatment of proofs appeared in the CPP 2018 paper and then in the 2022 JAR paper. This summer, I gave a 2-hour tutorial on CDSAT at Computability in Europe, and I wrote an expository paper that explains it in very simple terms, I hope. And we are writing a manuscript on CDSAT for these predicate sharing theories. Well, it contains the general result of completeness for predicate sharing theories, and then it applies it in particular to arrays, maps, and vectors with abstract domain, where we have these theories that I presented here. We had a first version at SMT 2022, and then there has been many development, and the long version is in preparation. Thank you very much.
So I very much understood and liked the arrays and the vectors, but I had an instinctive reaction against using lengths with a map, because the keys of a map are not necessarily ordered in any way. We have the size, that's fine, but...
That's true. And they are not even consecutive in memory.
Yeah.
We don't require that. We don't require indices to be ordered, neither for arrays nor for maps. Only for vectors we do, because for vectors, since the data structure can grow by a whole bunch, we need to say those that are in between. Maps, no. The growth may be just anywhere, just add the value somewhere, but doesn't have to be contiguous.
Okay,
And also for arrays, we don't require the interpretation of indices to be ordered.
And I think, to be honest, Python has a len operator that works on maps, just because the name was already used.
In the case of vectors, you also share
the ordering on indices. So for arrays and maps, we only need to share admissibility. For vectors, we need to share admissibility and disordering on indices, which, however, does not need to be linear. Unlike most theories which require the indices to be integers, linearly ordered.
This is a very particular question, but my dynamic arrays can grow linearly, or they can chunkwise, or they can grow exponentially. How much work would it be to adopt your theory to model that? Not too much, I think.
So you would like to model the speed of the growth? The rate of the growth?
If you assign something outside the array, you double the size of the array until your new index is inside the array. That gives you constant, amortized constant time access to dynamic arrays. That's why you have this exponential growth.
I see. So that would have to be an extension of our theory of vectors. So we can grow by a whole bunch. And additionally, you would like the theory to model the rate of change, how it grows. I don't know, I haven't done it. We would have to add axioms to capture this additional knowledge.
Or maybe not.
Maybe not.
Well, this could be on the index series that you would do that.
Oh, that's true. Thank you.
And in the index series, you could, I think that linear arithmetic plus times 2 is plus doubling is still decided. So
that's true. Because admissibility is not defined in the theory of the data structure. It is defined in the theory of the indices. So this additional work would have to be done there. Yes.
So you have this very nice flexible theory of arrays. I wonder if I'm doing an implementation, who decides like what theory is used to interpret the abstract domain, and do I need to have different implementations depending on which theory is used to interpret or how I interpret the abstract domain?
Well, the abstract domain is just a formula. So when the domain becomes concrete, it means that we are given interpretations of the sorts. So if arrays have indices that are integers, then that will be what we are going to use.
Okay, so one implementation for the theory would be enough in my CDSAT solver. Or do I, if I say I want to solve a formula where I interpret the abstract domain with
something else,
integers, then or with something else, then I need a different implementation.
Well, the implementation of the theory of arrays will be one, but the implementation of the theory of the indices will be different, and then we'll have two different combinations. So yes, then will be multiple theories to do that job.
Any more questions?
To your intuition, where is the decidability frontier?
Decidability for?
Frontier. The frontier of decidability in this theory of arrays. So you have the impression that concat will not make that indecidable, right?
I don't know yet. For now, I only studied many results that exist in the literature about concatenation. For example, there is a paper on JAR by Appel and Wang. They gave already a theory of arrays with concatenation. And they also gave an example where it is undecidable, but involving quantifiers. Because with that theory, they show it is possible to formulate the halting problem for 2 counters machines, and then it is undecidable. However, the formula uses quantifiers, so they didn't say anything about the decidability of the quantifier-free fragment, which is what we usually work with in the theory of arrays, and it's already a lot with respect to the theory of sequences where the decidability is not known. So if we add concatenation, I still don't know whether it is decidable or not, but I don't have any counterexample excluding it for now. And the one that I know for arrays with concatenation involves quantifiers.
Okay, any more questions? And let's thank the speaker again.
Zwei Punkte.